Good afternoon and welcome. My name is Jeffrey Porch, and today we'll be talking about IPv6 basics, or V4 and V6 basics, I should say. Kind of some of the reason for that transition, how that transition works, and again, a little bit of the in-between, get an understanding of how IPv4 works, because that's honestly likely what you will be working with today. Get a little bit of understanding of how IPv6 works, because inevitably, if you're going to find yourself in some job in the networking field, you'll have to understand IPv6 sooner rather than later. All right. Now, honestly, I always like to start with IPv4 because when you're looking at, again, where somebody will realistically work with IP addressing today, IPv4 largely is the option that comes up first. All right. So IPv4 is a system that's been around for quite a long time. It's well rooted in pretty much most of our networks. Although I guess that's going to be a little bit of an unfair introduction because even IPv6 has been around since the 90s. Not that makes it the most common addressing today. All right. But when we're talking about IPv4, all right, you have to understand that the purpose of an IP address is to basically make sure that your computer has a reachable address, right, in order to send traffic. Something that can come up here, of course, is going to be the idea of a MAC address, right? But when you're talking about networking functionality and the purposes of your multiple addressing, where IPv4 and IPv6 are, I should say, alternative configurations, there's generally not a reason to use both on the same message, with maybe some exceptions we'll talk about later in this webinar. MAC addressing is just used for an entirely different purpose. MAC addressing is more used for the local, how do I reach my kind of next neighbor on my network. IP addressing is more used for, well, how do I reach a device anywhere? And of course, there's a lot of exceptions to, well, what would break up a line of communication from some point A to some point B. However, again, IPing is still, or IP addressing is still going to be the method regardless of version. But when we're talking about this address, it is going to be broken down kind of similarly to how your street address may be broken down. When you're looking at the idea of like, hey, I live on, 123 Elm Street, all right? You can distinctly see, okay, I live at 123. That's my house number. That's how they can find me in that range. And I live on Elm Street. That gives me a rough area as to where I can be found. Now, unfortunately, unlike your street address, which can simply be read and just go, okay, yep, got Elm Street, I can find that. I got 123. Once I'm on Elm Street, I can find that. IP addressing is all numeric, right? I could have an IP address like 192.168.1.5. And without knowing how to break those down, well, if I just said again 192.168.1.5, it'd be hard to say, hey, what's the house number, if you will, the host portion of that address, and what is the network portion? All right. So at that point, it becomes hard to understand exactly where are we at in our address. But the first thing that you're going to need to know in order to approach basically that type of addressing and how to read it is the idea you have to have a basic understanding of, at the very least, binary. All right. Both types of addressing ultimately break down to binary. If I was to try to be realistic about this, you're more likely to run into binary and having to actually understand binary math. All right. I honestly realistically end on a potential, CCNA exam, than you are hexadecimal math. I mean, not that there's not time where understanding hexadecimal can be beneficial, all right? But, if I'm just talking about which of these is going to more directly lead me to understand the addressing, like understanding the binary is definitely going to help me understand, say, IP addressing, subnetting much more than hexadecimal. Because at the end of the day, subnetting is based around the binary. And even though IPv6, not IPv4, will use hexadecimal numbering, a hexadecimal format, right? Meaning you'll have 0 through 9 and A through F to give it a more dense form, mostly because IPv6 is already a very long address as is. And they want, we'll talk about this later, but multiple ways of shortening it. Again, you're not likely to actually have to like break something down from hexadecimal to binary in real life. Now, admittedly, especially because Cisco likes to test some of your core, fundamental skills, occasionally they will throw things like hexadecimal conversion questions on you, make sure you actually understand the numbering system, which, again, when you're talking about a more technical exam, kind of makes sense. But again, binary is definitely the more important one here. Now, to give an example of what we would see for subnet masks, right, which are these identifiers for, again, basically where the network and where the host portions end and how they tie to binary, and again, just how to read an IPv4 address, a modern IPv4 address. We have this example here on the screen. All right. So you see we've got 10.1.67, which is broken down into binary there. All right. And you see with a subnet mask of 255.255.255.0 or /24, which is really just a shorthand because, well, as you can imagine, if I had to sit up here and say 255.255.255 or a similar number again and again and again, that's just a lot to say, or in some configurations, it's a lot to type or read, or, well, I think you get the point. But let's talk about reading these masks. So, like I said, it's all down to the binary. If you actually look at this portion here, which we also tried to gray out a little bit, make it a little more distinct, you'll notice that when you convert 255.255.255.0 into binary, it's all ones followed by all zeros. This is the mask part of your subnet mask. What are the masked bits? So here, when you're talking about binary, right, you're talking about powers of 2, right? You're talking about basically turning on different values in order to create a new value, in this case, 255. So when you're talking about a byte, or technically with IPv4, you kind of call it an octet, every individual number broken down into binary, you are just going to end up looking at these, well, in this case, ones or zeros, right? But all ones in this case, and basically mapping them over 8 powers of 2. All right. So I could take any amount of ones and zeros, map them over what I generally just call a binary line for quick reference. But again, powers of 2, doubling. In order to understand what a value is. So when you're talking about 255.255.255.255, or 255.255.250 rather, apologies, that's where you get a value like this. Because if I add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, right? 128 plus 64, 192, 224, 240, 248, 252, 254, 255, right? Just adding all those values up. So again, 255, 8 ones. All right, because it's just adding up all 8 of those values on the bottom of the screen. And, we're doing it 3 times because we're looking at what are called, again, 3 octets, or more generally in a computer sense, 3 bytes. All right, out of our 4 octet or 4 byte IPv4 address. So that's the mask. All right, it's some number of ones followed by some number of zeros. All right, in this situation, this 10.1.1.67, since we have 3 octets of ones, that means we have 3 masked bits here. All right, which are going to ultimately, again, make up our network portion. All right, so you can honestly, especially for a simple subnet mask, look at the just here is my my ones, here are my, again, really 255s, because you're not going to likely be breaking it down into binary for this particular example once you understand what you're looking at. But I can say, hey, if I've got 3 octets, right, 3 numbers of 255, then that's going to mean I've got three numbers, three octets of my network portion. So my network portion here is going to be 10.1.1, right? That's I'm on the 10.1.1 network, or for my previous example, that's I live on Elm Street. All right. So at that point, when you're talking about again, just trying to understand, trying to read this address, this is like the area you're in, right? That's the purpose of networking, is trying to get to a generalized area. Because much in the way that you navigate just real life, driving from street to street or walking, whatever, you're not going to just try to say, let me head straight to this building, right? You're going to have to navigate, especially if you don't know where this area is, or the exact location of a residence. You're going to have to go to the general area, say, okay, let me get to this street first. And now once I'm on that street, let me get there. Now I know when you're driving, there's usually a lot more potential, say, alternative paths than in networking. But still, I think just as a, excuse me, pardon me, as a parallel, you can definitely see some, again, overlap there. All right, so we have to know what network we're on so that when you're talking about routing, right, and actually getting from one network to another, whether it be local networks or over the internet, it knows the general area you're in, right? And again, where am I? The 10.1.1 network. Now, at that point, the other portion, right, the leftover number, the .67, that is our host portion. All right, that is going to be, again, where I am on that network, right? I'm host number 67. Now, unlike a street, you don't necessarily see IP addresses assigned sequentially, all right? Meaning, just because, you go house 1, then house 2, then house 3, or again, just how houses would be numbered on your street. You're instead going to see, of course, different IP addresses change over time, get assigned not potentially in the same order, a lot of them being, even if it is sequentially, doesn't mean that like the two devices are physically adjacent, right? One could be, one room on your network, one could be, 3 floors away. It's all entirely dependent on how your network is set up. However, of course, your networking devices, your routers, your switches are trying to track where different IP and MAC addresses are in order to say this is where this device is. So, inevitably and generally pretty quickly upon joining a network, right, your device will be discovered, an IP address will be assigned if it doesn't already have one. And again, you'll be able to say, all right, you are this number, whatever it may be, 67 in this case. Now, when you're looking at IP addressing here, we are going to see options, right? Because if that was the only division, then there wouldn't be much more to talk about here. So if I were to put focus on this whiteboard, and again, we have our 10.1.1.67 example, right? Over 255, 255, 255.0. Again, I can draw that imaginary line right there, say everything on the left is the network, everything on the right is the host, as we just did. All right, but I could take another example, say 172.18.5.20, completely arbitrary set of numbers that I picked there, but I could give it a slightly different subnet mask, 255.255.0.0. So at this point, having removed an octet of 255, all right, I'm going to, well, basically shift where is the network and where is the host portion. So for this example, again, I draw that little imaginary line right there. My masked bits networking are now just 172.18. My host bits are 5.20, right? I've doubled the amount of host bits that I'm using, right? It was just previously 8, because again, remember these break down into bytes, 8 ones and zeros. Now it is 16. All right. I could even go a step further. And again, another arbitrary example, 10.5.5.5. right? Use a mask of 255.0.0.0. Do the same thing. Imaginary line. Right? Say the 10 is the network portion. I'm just on the 10 network, and I am host number 5.5.5. All right. That means I'm going to, again, have a much larger host portion, although as a direct trade-off for my network portion. Now, I have been asked before, well, why? Like, what's the purpose of using one mask versus another mask? And the short answer is, well, how large is our address space and how can we use it? You only have a limited number of IP addresses with a 32-bit address, right? Again, 8 times 4 here. You are talking about roughly 4 billion addresses, minus, reserved ranges and other limitations. We'll talk about some of those here today. But, and this is going to be some rough math. But if I was to, for example, look at this first example, the 255.255.255.0, right? I could say that I could create roughly 17 million networks with 3 octets. All right, and have technically 254 hosts per network. Right, that's per network. That's not clear. All right. Talking about the bottom example, just 255.0.0.0, again, now only giving 1 octet to the network portion. Now it's flipped. We've got 256 networks we can create, 0 through 255. And as far as hosts per network are concerned, we'll have roughly 17 million. All right. With our example in the middle being, well, as in the middle as exponential math can be, right? Looking at roughly 64,000 networks of roughly 64,000 hosts each. So at that point, when you're talking about why would we use one mask versus another, it's largely due to this. How many hosts do I need, right? And how many networks do I ultimately need to be able to create? Now, of course, if you're a small business or like in your individual home, this really isn't much of a concern, right? You can probably just be assigned any random network with, even just 200 or some hosts, and you're probably not going to exhaust that. As times change, that may change, especially as smart technology becomes more and more prominent, right? It is, over the years, gone from it being normal for there to be 1, maybe 2, right? Then you get up to, I don't know, 5, 6 when you're talking about multiple people having their own computers or laptops, you start introducing smartphones to the mix. You start introducing, smart light bulbs to the mix, game stations, TVs, appliances, whatever it is. So even like home networks are growing in scale, right? You put that in enterprise, and you have to be really curious, where does that end up in the long term? But still, again, the basics still hold true. You're looking at, well, how many hosts and how many networks. And with IPv4, this is our general, approach, or I would even argue main 3 subnets that you could assign. Now, a couple things I do still want to add here. When we are looking at, again, that shorthand that I brought up earlier, so seeing something like a /24/16/8, this slash notation or CIDR notation, we are looking at basically the shorthand by counting the number of bits. Because as you may recall, when you break 255 down into ones and zeros, or really all ones, that gives you 8 bits. And if we have 255, 255, 255, 8 plus 8 plus 8, that gives us 24 on bits, right? If I look at that for, the middle example, 255.255.0.0, that's 16 on bits, right? 8 per instance of 255, right? Last example is only a /8. So we have these shorthands, again, just to make them easier to read or say or whatever it may be. Granted, a lot of configurations are only going to accept your subnet mask, right? Typed out fully, 255.255.255.0, whatever that may be, or, whatever your subnet mask might be. Now, one thing I do want to say is, like, even here, we are only scratching the surface, only so much time to cover things. But we do have, again, anything 0 through /32, right, for these subnet masks. So at that point, I could, for example, throw up a completely different subnet mask. Well, if my drawing tablet didn't just crash, that's good timing. Say a /27, right? And it'll have a different size network and host portion. To bring up a chart that I ultimately teach my students to use inside of our class, we end up looking at anything between a /17 and a /32, which is basically third and fourth octet subnetting, in order to basically understand how you can manipulate these networks. And we're not going to have time to break this down in depth, but here you can even see, if I focus on, kind of arbitrarily, say a /28, that's going to give me a just particular slice of, subnets, right? So one thing I can look at is, it's got a binary of 16. So really what that means is everything is broken down into 16 bit portions. So here, let's get this backup tool that I have up and running. Always got to have a backup. So if I've got, my different address ranges, we can talk about 0 to 16 to 32, right? Because again, the binary being 16 in just this particular column, right? Which again is why binary math ends up getting involved. You have to break things down into binary, understand which binary associates with what subnet mask, right? I can go in and look at it and say, okay, well, 0, 16, 32. Let's actually add 48 in there because we're counting by 16, not doubling. But what I can, do is basically use these to create ranges and say, okay, well, if this range begins with 16, this range is 0 through 15. All right. So at that point, this range would be through 31, this would be through 47, this would be through 63, and this count would keep going all the way up to 255, right? The highest number we can get. But now we've got different ranges that we can break down, not just a look at the IP address, the subnet mask, right? And then kind of logically guess like, oh, okay, this is where we can draw that imaginary line from moments ago. Now we can actually mathematically break them down into different size of addresses. And that's where I would have you focus on the host row, where basically you're going to see, again, just 32,000 hosts to, well, technically this would still be 0, but down to 0, with 2 hosts being a /30, a peer-to-peer network, maybe just one router pointing at another router. All right, but at that point, when you're looking at, again, IP addressing and how it can break down, you've got a lot of options, as long as you're willing to stick to binary math. Again, everything here is based off binary. This is all looking at powers of 2, right? So at that point, again, we're just looking at like, hey, I can have 16 addresses per network. I can have 32 addresses per network. I can have 64, 128, 256, right? That's what that top line of this chart represents. Now, I will say something interesting is you do generally lose 2 hosts per network, all right? So, talking about 6 hosts on a /29, but 8 is the binary, is the number of IP addresses, but still. All right. But again, that's kind of the rabbit hole that subnetting can certainly go down. All right. These 3 are just some of the, I would argue, beginner options, right? Especially if you're not trying to maximize the number of IP addresses that you're utilizing. Now, why does this matter? Well, the short answer is, in order for 2 devices to communicate directly, they need to be on the same IP network, right? So you have host A and host B here, both on the 10.1.1.0/24 network. They can just talk, right? Similarly, if I pulled my internet connection, as long as I set up all the IP addresses in my house to be within the same range, whatever that range may be, then they can communicate without having to go out to the internet, right? This is an internal network. There's no, honestly, at that point, there's no even need for routing. Even a traditional router isn't necessary. I could hypothetically take any router out of my network. I could get just a switch, right? Plug these devices together and get some functionality. Now, admittedly, even though that is logically how it is designed to work, of course, as networks have evolved and gotten more complex, a lot of devices just assume the existence of a router. So, of course, taking a router out of your network may cause other problems. But just as far as like base network functionality, it is designed for, hey, if you're only staying local to your network, you don't need to touch the router. Everything's got the same IP range. Now, of course, if you had a device that for some reason you went in and manually assigned a different IP range, that's not going to work well with the other devices. So like if that host C, 10.1.2.0, was not connected through a router, but say through a switch, the other devices would see its other IP address or see that they're being told to reach a different IP address and just basically assume, oh, that's on a different network, I can't reach it. All right. However, obviously with the use of a router, which, any given network is going to have a router these days, I guess with some rare exception of very small localized network, you're going to have to go through your gateway, right, that router, in order to route between local networks. Very simplified routing, but still, you need one device that says, hey, Elm Street's over here, Pine Street's over here. The 10.1.1 network and the 10.1.2 network are over these different interfaces, whatever they may be. All right. And the router, of course, also needing an IP address in those ranges, right? Whatever that range may be, being 16 addresses or 17 million addresses. All right. Now, there are defaults to these addressing. Well, I was going to say an IPv4, technically not quite accurate. There are these classful defaults that only exist in IPv4. This approach to classifying our IP addresses is very specific to IPv4. IPv6 still has defined ranges, but you don't generally hear it as like Class A, Class B, Class C. Maybe more given, I don't know, more technical names, I guess would be a good way to see it. But here, when you're talking about your routable addresses, all right, we are generally going to look at classes A, B, and C. So at that point, basically anything with the first octet, so the first number of the IP address, 0 through 223, minus a bunch of reservations, is going to be a traditional routable address. All right. Now, admittedly, there are a lot of reservations. It's actually why, and I do this in some of my classes, I'll actually ask people like, hey, can you tell me what the public, right, the globally usable IPv4 range is? And the question's not easy. Even I, having many years of experience here, cannot concisely answer the question. Not because I don't know the answer, but because the system was designed in a way that essentially you can't concisely answer. Because basically what they did is they took this range, 0 to 223, class A, B, and C, and they just said, well, this slice is for this slice is for this slice is for this. And it kind of ended up a little inefficient. One thing that IPv6 does actually kind of address is that inefficiency. But again, these are our different classes of address. They have different first octet range. So like that 10.1.1.67 that we talked about earlier would be class A, because 10 falls between 0 and 127. And what these do give us is different default masks, meaning especially when you're in a situation where you're not trying to maximize any IP addresses, you can just basically fall back to these default masks in a lot of situations, just have assumed network sizes and go. All right. Now, there are notably two other classes here. There's multicast. Multicast is for another type of messaging, right? Because while a lot of messaging is unicast, one-to-one, some messaging, you could call it parallel to this Zoom meeting, this webinar, where I'm going to talk to all of you. That is one to a group, multicast, right? Maybe that group is all routers. Maybe that group is all routers running OSPF. But either way, multicast is one to a group, where unicast would be if I, singled you out one at a time and said, hey, talking to just you, only one of you can hear me, one-on-one. Now, there is another type of addressing in IPv4, broadcasts. Broadcasts are just going to be me shouting out to the void. Anyone who can hear me can hear me. Arguably, if this was a looser format, we could compare it to a broadcast, because honestly, the way the devices handle broadcast, if I am broadcasting out on my network, if I have one computer here, computer, in another room, computer in a different room, right? They would all hear the broadcast. They would just ignore it if it wasn't for them, versus multicast, which is a little more directed. Now, admittedly, Class C was reserved for research purposes, especially because they never, well, when IPv4 was existed, they never thought they were going to use all of this address. So it kind of just put a slice of the pie aside, and it never truly got thoroughly used. All right. Now, and this is something I kind of already mentioned, when you are assigning addresses, you have classful and classless IP addresses. All right. Classful addresses are following that default, which, especially for simpler networks, are networks, decades ago, back when, running out of IP addresses wasn't a thought in people's mind. Networks were created just classfully, meaning like we didn't have to care, right? Even enterprise networks, right, back in the day were not uncommon to be classful, and still today, smaller, medium-sized businesses, you'll see a lot of classful networks. But if you need to maximize the number of IP addresses, that's where classless IP addressing or subnetting comes into play, right? Using those different network sizes and ranges that I referenced in order to, well, facilitate communication on more controlled scale. That's actually where you may hear even another term, VLSM, variable length subnet mask, which is using whichever subnet mask is essentially needed for a particular network when you need it, right? Don't use a consistent networking size across the board. Use whatever size you need for the situation. If I've got a network that I know will never be more than 8 PCs, all right, then why assign it 200 IP addresses, right? IP addresses are very much so like reserved parking spaces. If they're even remotely assigned, they are assigned, right? Once that network range is established, that whole range is effectively reserved in a way. Variable length subnet mask is just saying, hey, use whatever size you need for that section of the network. So again, at the end of the day, if I just have two routers pointing at each other, right? This router talks to this router, and there's no other real communication on that network other than router to router. Why not just use two IP addresses, that /30 network that I briefly referenced earlier? All right. Why have more than two hosts if I only have two hosts? Well, host being router in this case. Now, there are certain reserved ranges, and we're not nearly going to talk about all of them, that you honestly do want to know, both in real life and on, say, CCNA. I will say that this range of all the reserved ranges I can talk about is probably the most important, although this range is technically 3. So private IP addressing is one of the holdovers that we have in order to prolong the life of IPv4. So here they took a range from each of the routable classes, A, B, and C, and basically said these can be used inside of every network anywhere, but they can't touch the internet. It's like an apartment number, right? If everyone hypothetically lived in apartment buildings, right, which is a good metaphor or analogy, I guess, rather, when you're talking about networks, because most networks are many things all in one building, not just like a household, which is very few. So if I said I lived at, apartment A, right, then that's unique to that building. Everyone else, listening to this may also live in apartment A in your building, and that's fine as long as there's only one apartment A or, apartment 101 or whatever it may be. So basically these three ranges, the 10 range, all right, literally anything that begins with the number 10, the 172.16 through 172.31 range, and that is 172.16, 17, 18, 19, right, all the way up to 31, all right, including 31. So technically it goes up to 31.255.255, just short of slash, or not slash, I'm sorry, I misspoke, dot 32. That is also a private range, all right? This is actually usually the one that I see people make the most mistakes on because it's not just a remember the 10 network or the 172. No, you have to remember it's 172.16 through 31. All right. And arguably one that you can see very commonly, the 192.168 range. But again, basically any computer today is designed to say, if I see one of these addresses, I know this is a local address, not a public IP address. All right. But again, these private IP addresses are a holdover because, well, again, IP addressing in total, ignoring reservations and restrictions, only has 4 billion addresses. And I want to say, and it's been a little while since I've done this a deep dive here, but like last time I checked, and different surveys, different research has produced different answers. I've heard that there's anywhere between 10 billion and 40 billion IP devices today. So anywhere between 2.5 and 10 times as many addresses as IPv4 can support. So even though they made the internal-external separation where you have private IP addresses inside and then public IP addresses on the internet, right, say like representing your house or the apartment building, in my example, we're still running out, all right? Now, but before we get into IPv6, I do want to talk about just some basic, commands for troubleshooting or understanding, your IP address on your own computer, especially if we're talking Windows, which I usually use Windows just because, well, very common OS, obviously. You can talk about ipconfig or ipconfig/all to give you your different addresses, anything from your MAC address to your IP address, your subnet mask, know what your gateway is, your router. If you're talking about Linux, you might talk about like ifconfig, or there's even just the IP command there, right? It can really depend on which operating system, which version of an operating system you're running. They all have, similar commands. In the Cisco world, you have commands like show IP interface brief, all right, which is again going to show us the status of the interface and that IP address that's set. One kind of limitation here, however, you do see it's 192.168.1.1, and maybe that's using the default mask, but maybe it's not. So using show interfaces can be a beneficial command when I also want to understand what is the IP range, because see, this one's a /30, which, as mentioned before, that is a peer-to-peer connection. So at that point, I know that this link only is using up 4 IP addresses, which again is 2 hosts. All right. Now, I do want to briefly talk about IPv6. Again, some of its basics, admittedly a little less than IPv4, because again, IPv4 is really a lot more likely what you're going to be using unless you're in specific situations. I'd argue most organizations dealing with IPv6 directly are either, large scale ISPs themselves, or honestly, a company doing what you should probably be doing, which is transitioning to IPv6. All right. But IPv6 has very similar addressing, or I should say communication, to IPv4. It's got unicast, it's got multicast, pretty much unchanged. All right. Different, addresses are used, but still the type of communication is unchanged. Now, however, where IPv4 had broadcast, IPv6 has essentially ditched that for anycast for 2 big reasons. One, basically broadcasts are not that efficient. They're not that secure. A multicast can essentially be a more efficient and secure broadcast. All right, so most protocols over the years, even honestly towards the end of like IPv4, well, the end, we still very much so use IPv4 today, but towards modern use of IPv4 protocols, they largely have switched to multicast. Not that broadcast isn't still used, but in some examples where multicast doesn't work, there is anycast addressing for IPv6. This is that almost a broadcast 1 to closest. All right, basically who can hear me. You have to think about it. If I want to go to a post office, I don't need to go to every post office. I don't need to go to every post office in my county even, right? Anycast is the idea of like, hey, regardless of where I am, I want to hit the closest blank server, right? Just for arbitrary example, I want to go to the closest post office. I only need to go to the closest one. I don't need to reach out to every post office, but that's an Anycast. Now, IPv6 addressing has a 128-bit address. And by comparison, again, IPv4's 32-bit address had 4 billion total numbers, right? IPv6, 128-bit, has 340 undecillion addresses, all right? Which is something like 340 trillion, right? You are talking about a magnitude of addresses so much larger that I literally cannot quantify it in a meaningful way. I told you the number, right? But like, that's meaningless. A human being can barely understand what a million or a billion of something is, right? Like, yes, obviously on a conceptual level you can, but like, I don't know, it makes me think all those like infographics where they try to compare like $1 million to $1 billion and things like that. But like when you're talking about 340 undecillion, it's a lot. But again, this was the main purpose of IPv6, to get around that restriction of IPv4 having a limited number of addresses, and again, basically designing it to, well, not require additional addresses anytime soon. Now, and admittedly, I'm going to end up skipping this slide because I'm going to go towards the visual here. But when you're talking about IPv6 addresses, this can, of course, lead to longer addresses, which is why we create shortcuts. And again, a well-designed network will keep these shortcuts in mind, try to intentionally work with them. But at the top there, you see the full written out example of an IPv6 address, right? Hexadecimal, right? 0 through 9, A through F. All right, 8 sets of characters, 4 hex each. Now, the second example, and very notably here, these are different examples, right? So this example is one different example. This second, you can kind of see the gray in the middle, is a second example, even though the addresses are similar. I didn't convert from the first row to the second row. I changed the addresses. Notably here, you see I made this into 00AC. Well, just like if I was writing you a check, you don't care how many zeros are in front of the check. All right, we can just write that as AC. However, if I was writing you a check for, let's call this $9,000, although this is 9,000 in hexadecimal, very different number. If I talked about trailing zeros, and I said, hey, if I'm writing you a check, can I drop those zeros in the back of the address? You're going to say no, right? Because that obviously changes the value of the number. Hexadecimal is no different. But for IPv6, you can drop any leading zeros. Additionally, if I have groups of all zeros, something that I can do once and only once is I can replace zeros with a colon, basically saying insert however many zeros are missing here. Because again, when you're talking about IPv6, we said we need 8 sets. So taking this example for now, I see 5 sets of numbers, right? The 2001, the zeros, the 00AC. And that means that I must be missing 3 sets of zeros. Or the bottom example, where I should see 7 sets of numbers, not exactly saving us a lot of space. So that means I'm missing 1 in that colon. If I had, an entirely different example, A colon B, that means I've got 2 sets of numbers, A and B, and that means I'm missing 6 sets of zeros in between. So this is a very convenient way to truncate an IPv6 address. All right. And again, realistically, so you don't have to write out that whole address there up there at the top, although of course copy and paste exists. We would be kind of making our addresses biased towards let's truncate these addresses. All right. Now, this has also been made easier by the way that they designed IPv6 reserved ranges. All right. So here we can talk about, unique local ranges, which is anything that begins with FC or FD, all right, which are the equivalent of private IP addresses. They can be used internally. But at that point, if on the left-hand side of your address you see FC, FD, it's private. Unlike IPv4, where you have to remember the 10 range, the 172.16 range, which is, again, slightly more drawn out, and the 192.168 range. You say, nope, FCFD, right? These first two characters, there you go. All right. Even the public IP addresses is anything 2 through E. So at that point, again, I still couldn't define for you concisely what a public range is for IPv4, because again, basically they had this whole range and then they just cut different slices out and they said the public is whatever's what's left. That's not the case with IPv6. IPv6, you're looking at 2 through E. All right. You also have link local. Link local is kind of a new type of address for IPv6. It's used for kind of local management of that link, hence link local. All right. So at that point, it's used for neighbor discovery, which is similar to ARP, translating between IP and MAC addresses. It's used for router discovery, right? Talking to local devices. It's used for discovery protocols. It's used for local communication on that link. All right. Again, it's more management style interface than your traditional routed interface. All right. But that's always going to begin with FE80. All right. And then you've got multicast. That's going to always begin with FF. All right. But it is the range of FF through FFFE. Okay. But again, more reserved ranges. And I will say more concise than IPv6's reserved ranges. If you can really just remember really no more than 4 characters, usually 2, because even with FE80, if I can just key off of FE, like that will work in most situations. IPv4, you do just have to remember a bunch of different ranges, and you do have to remember their variable ranges of variable length. Because of IPv6's much more, well, extensive address space, we are once again back to, we don't really need to care. Because I think even if you break an IPv6 address in half, which honestly, when you're talking about subnetting with IPv6, which technically the mechanisms are there, but they're rarely used because you don't have to care, right? Like if you just, again, break a network in half, left half is network, right half is host, similar to IPv4, just host network. Like that's something like some number of quintillion networks with some number of quintillion hosts each. More than any modern network could ever use, right? But still, the entire world could fit on a single IPv6 network. Not that that would be efficient, right? Because again, logical groupings make sense. Now, IPv6 address assignment is going to be similar mostly to IPv4 address assignment. You could statically assign the address, which is more common for network devices or servers, things of those nature, right? Where I manually go in and assign it. And I can use DHCP, a centralized server, to hand out addresses for me. Usually helps prevent duplicates. Great for bulk hosts, phones, computers, whatever they may be joining my network. IPv6, IPv4 basically has the same option. They're a little bit different, right? DHCP functions a little bit differently for the two because, well, 2 different addressing, but the core concepts are the same. Something that is added to IPv6 is stateless, or basically an assignment that's not tracked, called SLAAC or EUI64. EUI64, in short, is basically taking a MAC address of the device and using that to derive a IPv6 address, right? At least the last 64 bits. So they take the MAC address, which is a 48-bit address. They add this like buffer in the middle, FFFE, because, well, if it's half of an IPv6 address, it needs to be 64 bits. And basically at that point, it, well, makes up your host portion, right? The second half of your IPv6 address. And again, it doesn't need to be tracked because of 2 big reasons. One, IPv6 has so many addresses that even if no one server is tracking, no DHCP server, say, is tracking what address is where, then it can still just say, yep, nope, you're very unlikely to repeat an address of someone else. And 2, remember, this is MAC address derived. And we already are in a situation where MAC addresses shouldn't repeat. And if your MAC address does repeat with another device on a network, that'll already cause networking problems. So you would have already had a problem before a problem can show up here. If anything, this would make the problem worse, which is more notable, right? Easier to troubleshoot. All right. But again, this is a stateless assignment. Slack, again, basically, you don't need the centralized server necessarily with IPv6. But again, of course, you've got static assignment, right? With IPv4, it would have been IP address and then whatever the address is. With IPv6, it's IPv6 address, similar commands from a Cisco perspective. All right. And again, similar commands for troubleshooting too, right? Pinging still works pretty much the same, but instead of show IP interface or show IP interface brief, right? Show IPv6 interface or show IPv6 interface brief, right? Again, shows you the IP addresses. And do note IPv6 doesn't have so much of a restriction on, say, number of IPs per interface, so you might actually see multiple, especially with like link local and unicast addresses. Now, the last thing that I want to talk about before opening this up into kind of a little Q&A is do note that IPv4 and IPv6 are not compatible, right? They are designed completely different. They're very different addresses, right? It's basically like one half of your network speaking German and one half of the network speaking French if you tried to use both, right? Even if they could find common ground, they still can't really hold a full conversation, right? So how do we get from one to the other, from v4 to v6, ideally? Well, you've got dual stack. Dual stack is everything is configured with both. Everything gets IPv4 and IPv6 address, and during the transition, if there's any device that still only knows IPv4, sure, we'll use IPv4 during that communication. I'll just try to use v6 elsewhere. All right. Problem with dual stack is it can be, well, a lot of work, right? Because you are slowly assigning all routes, all addressing, right? Everything in both, right? It would be like, okay, if we're transitioning, I don't know why you would do this, but if we're transitioning from everyone speaking German to French, right? The interim is everyone learns both. Tunneling, on the other hand, tunneling is going to be when I've got, say, one network that needs to communicate with another, right? Like a v6 to a v6 network, but there is a v4 network in between. So tunneling would be kind of like a VPN tunnel. It's a logical direct connection of those tunnels. So what would happen is as the packet left the IPv6 network, it would add an IPv4 header to it to be tunneled over the v4 network. Once it reaches the other side, it would remove that header and basically, well, now be just IPv6 traffic again, right? The last one, which is more of a translation, NAT64 works a lot like NAT in general, where I could have a NAT server, usually a router, basically sitting between two networks, all right, facilitating that communication. So at that point, basically this translator in between is looking at like, oh, okay, I know, again, French and German, I don't know whether this is the language I'm picking today, but, and I can translate between the French network and the German network, right? So really it's for those last two, definitely two different use cases. Tunneling is when I have a network between two networks. NAT, the translating method, is when I've got one network talking to another. Dual stack works really well within a network when I've got just device to device communication. All right. But again, dual stack ends up being very configuration heavy. Not that all of these are easy. But again, we need to use some transition method as we are slowly going from v4 to v6. But at that point, that's what I have for you today. Again, that high level view of IPv4, IPv6, some of the issues. But I did want to open this up to all of you. Did I have any questions, comments, concerns about anything here before we wrapped up for the day? Well, I don't see anything in chat. I'll stick around for a couple minutes just in case anyone's typing something. But other than that, thank you all for attending. Hopefully you were able to learn some of the basics here. Subnetting is probably in itself an hour lecture to get any amount of deep dive into that. But again, hopefully this was informative. and enjoy the rest of your day. But have a good one. Yeah, my pleasure.